So thank you for the invitation. That's a beautiful occasion for talking here and for talking about this topic, which is something a bit strange, not very similar to many other things that I've done or that I've seen around. But I think it is somehow pertinent to the topics of this conference and this series of conferences. And it's a long time ongoing work with several collaborators which are all Italians, In particular, there is my former thesis director, which is Sergio Caracciolo, which is now retired, but is still working. And from a student of him, which is called Gabriele Sicuro. And Matteo D'Achille is here, but he's also Italian, in fact. And bits and pieces done with different people, it would be complicated to explain. And the title is very long. It was a temporary title, and I didn't update it. But it tells you the message. There is a famous problem. And this problem lives in a field of mathematics that we shall call functional analysis. It is the Monch-Kantorovich optimal transportation problem. You can think to it as a given instance. You have one measure, a second measure on the same metric space. You have a cost function, and then you want to optimize the transport. I will give you the definition in a second. And then there is statistical mechanics, which is what I did for a long while when I was in Italy, essentially. So in statistical mechanics, just like in probabilities, you calculate statistical properties of a problem which is realized over different instances, and the instances have a given a priori measure. And here the problem is so complicated and so interesting that the very obvious measure that I will tell you in a second will be the good one. It is useless to add other ingredients to the story. And so you want to understand the statistical properties of this problem in this realization. But given that you are averaging over the disorder, in statistical mechanics, you will call this a problem in spin-glass theory, in disordered systems. And as you are searching for the optimal transportation, which is the best one, you are searching for the ground state of the spin-glass. So this is, in a hidden way, zero-temperature statistical mechanics of disordered systems, which will be more comfortable for me. But nonetheless, it remains a problem which is either in functional analysis or in probability theory, fields of which I'm not quite an expert, so I will have a bit of troubles in comparing with existing literature, but I will take bits and pieces when I need it. So, what's the problem? Very simple. You have a domain omega. Omega will be compact and of volume 1. It will be Euclidean, in a sense. It will be a chunk of the Euclidean space in dimension d. Most probably a cube or a torus, the standard unit torus. You can think to that. Or a sphere normalized so to have surface 1, if you want something which is very symmetric, just like the torus. And on omega, you have a large n parameter. N will become large in a moment, because you want to do statistical mechanics, of course. And given n, you have an instance which is realized as a list capital X. Actually, I think I used small n for most of my notes. Of points in omega. An ordered list. So this is nothing else than, for example, in what I was saying, a square and a bunch of points over it. Then we define a special family of vector fields, which are called transportation plans. The set of transportation plans, that I call transportation fields because they are vector fields, for a given set X and in the domain omega, are the set of vector fields mu of x from omega to r to the d, in this case, if this is in dimension d. Such that two things happen. For all points, but in fact, all points up to a subset of Lebesgue measured 0. You will understand without all precisions. Y plus mu of y is, in fact, a point of x. So this first property defines a function j of y such that this point is in fact xjy, which is in capital X. So it will be x for some index j. Let's say that they are all distinct. Of course, things will go to the limit if we need it. If they are generic, there are no problems. And 2, property 1 defines a partition of this domain into cells. The cell Cj is the set of y's such that j of y is equal to j. All these Cj's must be all equal to 1 over n. Sorry, I put part of the definition into the condition, but you understand this. You want to split this domain into portions sometimes you are a bit unlucky. For example, you could do this. And so these points are 1, 2, 3, 4, 5, and 6. And these cells are, say, 1, 2, 3, 4, 5, and 6. It is not inconceivable, and in fact, quite probable in the Lagrange limit, that the points are not contained into their own cells. If two of them are right near, it is kind of clear that it will be hard to fit the two cells together and still have all of them of volume 1 over n.
So all the cells are of the same volume?
Yeah, we stipulate that. Or you can give probabilities, but they have to be fixed a priori. Which, by the way, is a difference with the typical Voronoi selection that you do, in which the volumes are what they are, and in which the points are contained. So, this is the transportation field. And the optimal transportation fields for the quadratic Monch-Kantorovich problem is the one that minimizes the cost function energy of mu being just the L2 norm. Dimension D, I don't put dimension there. You want to minimize this. The one that minimizes that is the optimal transportation field. The value of the cost is the optimal cost. And if you have a statistical average over x, this will give you...
No, you mean something else, because mu of x is just point in your definition. Maybe you mean distance from...
I took a flat domain. This means that the distance is the vector. So these are the values mu of y if this is the point y. But in fact, if you do that, for example, on a sphere, you don't use this. You have to use geodesics, and the notation gets messy, although the message is the same. And on the torus, you have to take the short one, not the long one. So this brings us to the notion of E of x is mean over inf, let's say inf over mu, which are transportation fields of E of mu, and E of n omega is the averages over x in omega to the n of E of x. So, very natural definitions. And if you fix omega once and for all, for example, to be the unit square, this will be some function of n. It is kind of easy to realize that this function should go down at least like 1 over n, but it may be larger. And the important fact is that the truth is that it is larger by a logarithmic factor. So, a theorem which will be the starting point of all this story is that En omega, in fact, essentially for all omegas which are decent in dimension 2, behaves like log n over 4 pi n plus dot dot dot, assuming that omega is volume 1. So the fact that there is a log n instead of a constant tells you that something non-trivial is happening, that a greedy algorithm will not be enough for understanding everything. You have to do some intelligent algorithm, which in fact exists and is essentially a variant of the Hungarian algorithm. And if you have transportation from points to points, it's just the Hungarian algorithm. In this case, you can use the Hungarian algorithm to approximate, or use a better algorithm that does that directly, but it's philosophically the same. But just like in spin glasses, where greedy searches don't find the solution, but differently from true difficult Sherrington-Kirkpatrick spin glasses, in which there are just no decent algorithms, here we have a polynomial time, not linear time, algorithm that finds the optimal solution, which is the ground state of a spin glass model, which is telling us that we are dealing with a disordered model of intermediate difficulty. It is complex enough that it's not a too stupid toy model, but it's simple enough that it has polynomial time algorithms for finding the ground state. And so you have a lot to learn on that. And that's also due to the case that a special feature of dimension 2 is that the model is critical at temperature 0, which is not uncommon. It is a long-standing fact in statistical field theories that critical phenomena may be defined on lattices, for example, in many different dimensions, like the easy model. And there will be a notion of analytic continuation in the dimension, and the notion of lower and upper critical dimensions. And in many cases, although not all cases, those values of dimensions are integers, although that was not guaranteed because we are in analytic continuations. But in fact, it often happens that things happen where certain integrals diverges, and integrals diverges typically because they are integrals of 1 over x. If they were diverging stronger, it would have happened before. So it is not uncommon that these critical dimensions are integers. It is 1 for the easy model, for example. It is 2 for the ON model, the O2 model, the famous vertex model. And there are spin glasses typically pump the critical dimension up, so it is not weird that it is 2. For example, an argument to see that is that, let's go back to that drawing, because there are many simple facts that you can establish by purely geometric arguments. And one fact is that these cells are not typically of this shape. These cells are polygonal cells which are close relatives of a Voronoi tessellation. I don't know. I don't really know how to complete it, but let's say this is the one. A normal Voronoi tessellation is what you get if you take the midpoints and you continue them up to when they hit. And you know what I mean. You do that in all possible ways. This was not very good. And this is what you get in this case, I guess. And the volumes are not those. They are not just 1 over n. Mm-hmm. But telling that this is the boundary means that the distance from here to here is the same as the distance from here to here, and it is smaller than all the others. But it is exactly the same to tell the square distance is the same. So now we introduce some parameters. We have our points, 1, 2, 3, and so on. And we have some real parameters, A1, A2, up to AN in R. And we say that the boundaries of the Laguerre Voronoi tessellation of parameter vector A is the set of cells that you get by telling that the boundary is so that you have a boundary between the cell Ci and Cj if the point y is such that y minus xi squared plus ai is equal to y minus xj squared plus aj, and smaller equal than the same expression with all other indices. So the a's are doing the modification with respect to the ordinary Voronoi case in which all the a's are equal to 0. The a's are defined only up to 1, adding the same constant to all of them. So you can say, for example, that they have 0 average. And which is the same as for looking at the volumes of the cells, because the volumes of the cells make n parameters, but in fact they are n minus 1, because you know already that the sum of them is size of omega equal 1. So we have n minus 1 truly free parameters here, and n minus 1 quantities to be fixed here, and there is in fact a function that you can locally invert, which is telling you that somewhere there is the good set of a's, such that the cells that you get by this recipe, they all have surface 1 over n.
So this kind of Lagrange multipliers, yeah?
Yes, but simple ones. And as I will introduce Lagrange multipliers in a while in a field theory, I don't want to use the name, because that would have made confusion. So this is it, and you see a trouble. Suppose that, as I promised you in the title, I want to treat mu as a field in a statistical field theory and work with it. There are a lot of troubles. Mu is not a field like a Gaussian field. It has a lot of constraints to satisfy. And second, even if I have it, suppose that I do ordinary things in statistical field theory, and then I go, for example, in Fourier transform because I do Feynman diagrams in moment space. Mu is not continuous. Mu here is this vector. mu here is this vector. It jumps. At least this function is continuous. Mu of y square plus a of j of y is somehow, let me just do a picture in one dimension. It's a bunch of parabolas which glue together. So it is continuous, but not differentiable on the boundaries. So we will see these troubles popping out in what you get as an expansion. So let me change Blackboard now. I have to tell you the history of this problem, but the history is very long and I don't even know it well. But I will tell you the history from what is my perspective. We know from the 80s that that log must be there, but the constant was not known. This 4 pi, the weird constant, was not known. In 2014, two similar papers appeared with similar authors. The one that I will mention is Caracciolo, Lucibello, Parisi, Sicuro, 2014. I don't know why I misspelled the Italian surnames. They have the prediction that En should go like 1 over 4 pi n log n plus small o of log n. But this is completely a physics prediction, I will say, in the sense that they do an approximation of which they cannot evaluate the consequences. Then they see that the troubles that they get in quantum field theory, in their theory, is like typical troubles that appear in quantum field theory and are normally solved there by introducing a cutoff function. So they do the same. They introduce a cutoff function and hope that the result that they get are universal, that is independent from the form of the cutoff, except for its very qualitative effects. In dimension 2, this is the case. In dimension larger than 2, this doesn't work. In dimension smaller than 2, this is not needed. So, not at all something that looks like a theorem. However, luckily enough, Caracciolo was in Pisa, and also Luigi Ambrosio is in Pisa, and they started talking together, and Ambrosio is a function analyst quite involved into this kind of problems, and so he thought about that, and when he was convinced that the guess was true, the idea was having some hidden truth inside, he developed a method for giving a true mathematical proof of that, and so they reached this result, but still we're not controlled. And slightly later, with Federico Glaudo, they could say that En is really 1 over 4 pi n log n plus something not bigger than square root of log n log n. But these weird error terms, they admit that it's due to the fact that their method don't control the error terms quite well. And they kind of claim that with their method, it's not just that they've been lazy. Their method intrinsically cannot do much better than that. And those are very good people, and if they say that their method don't do that, I will not use their method for trying to do that, because that's out of discussion, essentially. Nonetheless, I believe we have huge numerical simulations. The algorithm is polynomial. We have numerical simulation that tells that the error times are much smaller. They are possibly a log n, or just a constant. So we believe that there must be another way of proving that this error time is not there, and maybe calculating other terms in this series, which are interesting, because this one was kind of too obvious, once you believe that. For example, we had a paper at a point with the same author that I told you, Caraccio, Sicuro, and D'Achille, plus two others in Rome, Benedetto and Cagliotti, which is a long paper and makes a lot of stuff, but somehow under the same theoretical ideas of Caraccio, Sicuro, and others, we deduce that En and omega behaves like 1 over 4 pi n log n plus some function of n that doesn't depend on omega plus k omega the way I write it, plus little o of 1, where k omega is the Kronecker mass of the Laplace operator, which means that if we call lambda plus the set of eigenvalues with multiplicities of the Laplace operator, dropping the 0 if you are, for example, on a torus or on a domain without boundaries, then you have the zeta function of omega for the Laplace operator, which is which universally by Weil theorem behaves like 1 over 4 pi 1 over s minus 1 plus some constant plus something that goes like s. And this constant, we can call it the Kronecker mass, because in the case of the torus, it is given by the first Kronecker formula. So this is weird. We don't know exactly what this function is. This could have been this one, so large. But whatever this function is, if I do this experiment, for example, on a square or on a rectangle with the same area, and I plot the values of those, and I plot the differences, they really go to this difference of k omega minus k omega prime plus things going to 0. Weird enough, I don't know the behavior of any omega, but I know the difference of the behavior among any pairs of omega omega prime. However, this is just a prediction on the very same ground of the theoretical guesses that are there. So we also want theorems that explain this. And as the control is not given here, I suppose that these methods wouldn't work for this. So, what do we do? First of all, we kind of read back what Caraccio, Lucibello, Parisi, Sicuro do in a different terminology, in a sense. In my perspective, they do their approximation too soon, and they lose control immediately. But they could have written down an extra field theory and worked with it longer. So, in order to write in a decent way the field theory, you should work in finite temperature. And then work with the genetic function in finite temperature, which is the partition function. And the limit of temperature going to 0 will give you the ground state energy, as it always is. And the partition function has a form, a bit of this form. Given rho, this is somehow related to the functional integral over fields, which are generic fields, not field transportation fields. But then you have some Lagrange multipliers, which are a scalar field that will implement the fact that mu is a transportation field. And then you have an action. A complicated action, but still not too bad. If I write it in Fourier basis, it's a sum over momenta, which are in 2 pi z squared as set for 0. Minus 1/2 mu p mu minus p, as it is normal, minus the term implementing the constraint, which is phi p minus p, rho p minus this weird object, e to the minus ip mu p. By e to the minus ip mu q, I mean the Fourier transform of this function in q. And here I have to evaluate this Fourier transform of this function, which has the parameter p. I have to evaluate it in the same point, p. Well, if you write it in terms of an expansion, this is 1 minus ip mu p plus, well, minus I squared over 2 factorial, that's more clear. P dot mu q, P dot mu P minus q, and so on and so forth, sum over q. So it's something that if you write it in Taylor series, it's quite clear. Once you have it, you realize that the zero temperature limit is like a semi-classical limit. Beta is going to infinity means that the ground state is described by the fields mu and phi, which are the saddle point of the semi-classical equations, which is the Euler-Lagrange equation for this action. And once you have the Euler-Lagrange equation, you imagine that you can solve them, and you find the solution for mu and the solution for phi. You evaluate the integral of mu dot mu, and that one is the optimal cost. The optimal cost is the integral of mu dot mu over the saddle point of this quantity. The trouble is, of course, the Euler-Lagrange equations are formidably difficult to solve. And what you do is something that reminds a bit of statistical field theory in general, but not quite. In statistical field theory, you would have Feynman diagrams, which means graphs with external legs, loops, moments flowing on the arcs, rules for putting weights on the vertices, putting weights on propagators, and summing over everything. However, in this case, we will not have graphs. We will have oriented routed trees. This is not completely new. Something like this has happened a few times. For example, Parisi and Surlas in the 80s have studied the disordered lambda phi to the 4 model in a similar way before they invented a better way involving dimensional reduction. That is, they write the Euler-Lagrange equation, and they rearrange the terms in such the way that the fields that they want to find are written as a regularizing system. If you have an equation of the form A equal something known plus another function of A, you can imagine that this is interpreted as A is equal to f0 plus something that makes vertices. For example, suppose that this was 1/2 a square. Here you would have plus a square. So if you do this, and f0 is a constant, you get Catalan trees. So this would tell you that A is f0 plus, let's remove the 1/2, it's not important, a square. And then A can be f0 plus something. So it is plus f0 square plus 2 f0 cube plus 5 f0 to the 4 plus dot dot dot, which is a formula with square roots. This is a bit like this, but in a functional form, not just with a single function, but with a function of positions and everything, and with differential operators. So you interpret your Euler-Lagrange equations as a regularizing system for one given monomial, which is especially simple. And the Euler-Lagrange equation that you get are these ones. There are annoying 1 over p squared, but in fact, the p's which are there are only those which are non-zero, because the zero mode is fixed by the fact that the two original measures are normalized in the same constant. So those are never zero. The integrals may have divergences for p going to 0, but p equals 0 is singled out when p is considered exactly on the lattice. 1 over p squared, rho p, minus, sorry, there are many terms here. So this notation qk of p means for me the quintuplets q1 qk such that sum over qj is equal to p. It happens so often in your indices that you really want a notation for that. And mu of p is ip phi p plus sum over q iq phi q sum over k larger than 1. Same things that I have here. very big equations. They teach us two things. One, that if you do Feynman diagrams starting from this, you will have at least 3 types of vertices, a lot of factors, rules, factors at numerator, something weird. But they also show us that we have worked more with respect to the original Caracciolo, Lucibello, Parisi, Sicuro, in order to see how their result sits in the true theory. Because if you drop out everything that looks complicated, which means this one and this one and this one, you get their solution, which tells that phi approximately is the solution of the Poisson equation for ρ, and mu approximatively is the gradient of phi. So the cost is approximatively given by the integral of the gradient of the Laplacian inverse of the density square norm, which is a quantity that, unfortunately, on average diverges, unless you, for example, replace the delta functions with tiny Gaussians. And in that case, it is cut-offed with a cutoff that gives an extra factor, which is the logarithm of the inverse width of the Gaussian. If you interpret as these Gaussians to be somehow related to the typical spacing of nearest neighbors, this gives the log n, and the universal 1 over 4 pi is just given by the fact that the p's that are here, they are 2 pi z squared, and there are some simple integrals there, and the result follows somehow. But the point is that we don't need to make an approximation out of control. We can make subsequent approximations which are finer and finer, and truncate this series of regularizing systems at some degree, and hope that this one is giving better and better approximations. Too bad that this is not the case. If you do the diagrams, you have signs everywhere, and the amplitudes become messy. They get higher factors of log n at numerators that should cancel out if you could understand the exact summation of those diagrams, but you have to understand that exactly, and you cannot approximate, and as the integrals are very difficult, you will not be able to do that. What you can do, in the spirit of what Jean Bernard was telling yesterday, is to do a dressed theory. You understand that those extra logarithms comes from certain subdiagrams that you can symmetrize and then factor out, and when you factor out, they produce a very interesting mechanism. They produce a cutoff function self-consistently. The cutoff function is on a scale of the optimal cost, although you haven't determined it. That is, the optimal cost is a formal series of Feynman diagrams induced by this theory, but now dressed, and in which the vertices have a cutoff on the scale of the energy, the quantity that you are finding. This solves the problem of the logarithms and numerator, but it doesn't solve the problem that there are infinitely many diagrams contributing at the leading order with signs, and it's not clear that those are summable. So we do something different. That's the beginning of a story in which we work a lot, and we do theorems after theorems. And for example, at a point, we have a nice theorem, which is, well, you see, mu is only a function of phi. And when you replace for phi, sometimes you have rho, but sometimes you have the mu's. Let's say that when you have the phi,
Andrea, you have 5 minutes.
5 minutes, okay. I have to select the topic. Let me skip this and give you directly something. which is a result. So one nice result of this procedure, which is a bit involved, but at the point you get to that, is that you reach the following conclusion, that the energy, the optimal cost for a given rho is sum over p of something which is not very different from rho, which is the inverse Laplacian of rho. This is true for d equal 2. There are similar formulas with higher orders in higher d's. So after a lot of magic that I skipped for you, you reach a formula for the optimal cost, which is only a cubic polynomial of the keys. Keys are just, they are, it's a shorthand for the fees. So they are essentially the original quantities. And they satisfy a rewriting system which is only quadratics. It's very similar in spirit to the one for Catalan trees, except that you have those weird weights now. And these weights, you see what it is? I have to tell you this because it's beautiful, and then I will let you with this. Instead of having the horrible diagrams that you get from the original things here, you get diagrams that can be represented this way, as cacti of triangles. So you do trees by gluing up triangles. And at the boundaries, you have the rows. So those vectors are really moments, p1, p2, and so on. And at the boundaries, we have factors rho of p1. At the internal edges, actually at all edges, we have factors 1 over p square. And on the triangles, you have those factors which are area square times 4. And actually it's a minus 2 area square. The area is given by p wedge q. So look at the rewriting system. What is key? This is something that is telling you what is key. Key is either on the boundary of this cactus. So it's rho p or a sum over the possible ways in which you can put a q and then a p minus q, and there is a minus 1/2, and then you are going to have the new keys here, and what you have here is a q wedge p minus q squared, which is twice the area of this triangle squared. So it's such a weird theory in which the diagrams are trees obtained by gluing triangles, and the weights involve the inverse length of the edges and the square areas of the triangles. and then you average over the things that you have there. I don't know if you ever seen something like that, but this is what pops out of Monch-Kantorovich optimal transportation in dimension 2. That's a good point to stop.
Very nice point. Okay. Any questions or comments? This is also yours. Yeah.
So simple one. Your set omega belongs to R to power D. So your results are for arbitrary D in principle?
If you do these things, it works for arbitrary D. Okay. If you do these things for arbitrary D but finite, you will have polynomials in which the degree here is up to D plus 1 due to a very interesting mechanism.
Okay. And now for D equal 1, we have analytical formula, by the way, Italian one of Saldemini, which gives the optimal cos as a integrated difference of cumulative function. So how your complicated results go back to those known analytical results?
Well, we have worked also on D equal 1 as a toy model for a while, and also in this very long paper we do a lot of checks of our formulas against the exact formulas for D equal 1. And they all work, but the point is that sometimes that works because of subtle properties. For example, a simple check, something that should have been trivial, it works only if you at some point you realize that left-hand side is equal to right-hand side because Lagrange inversion formula exists. So even the simplest D equal 1 checks sometimes are subtle. Actually, they are a factory of identities. I found unsuspected identities just from checking something that should have been true in D equal 1.
Grazie mille. Okay. Maxim?
Yeah. It's about this constant k omega, yeah, for the area. If it's a torus, is it 0 or something depending on the shape of the torus?
It's a function of the shape of the torus involving the Dedekind eta.
Yeah, that's what I expected. And then it means that when you do this momenta, you make kind of like equal size x and y things. And because of your identity, it should depend, get like one parameter family or whatever you can.
Well, I've been so happy when I said the sum over momenta, I was sitting on the unit torus. And it is true that, for example,
you can change the scale because your function fn at the end of the day should be independent on the shape of the torus. And you can have summations of different lattices. Yeah.
My feeling is that fn is independent of the shape of the torus because it depends on the short distance properties of this optimization problem. While k omega depends on the shape because it is related to the Weil theorem, essentially. But this is, for me, an intuition which is very vague, and I wouldn't be able to really prove it analytically. It's just the reason why I believe that that is true.
Yeah, but in this summation of when you get 2 pi z squared, you can imagine square lattice, yeah? And if you change shape, it will be kind of different form for the same thing. Or?
I'm not sure that I will answer exactly to what you are saying, but what I was dreaming is not exactly what I get, but it's not far from what I get, is that this term only comes from the correction to this term in the very basic diagram in which you have only this. And all other diagrams are more regular and they do not depend on omega. So omega is the only, this is the only diagram where you see the logarithmic divergence. And all the other ones, once you do that well, they don't have the logarithmic divergence, and so they are independent from omega. You can sum. But I cannot tell that this is a theorem. This is just my pathway. One day will be a theorem, hopefully.
Okay, we have a time for last question. Jean-Bernard?
Yeah. I see these signs with minus 2a squared. So when you solve your system of equations by trees, don't these signs proliferate and make the discussion difficult?
Well, in a sense, they are the same signs that tells you that in other version of this talk, I tell you that the troubles that I have with these signs is like in the proper definition of this. When you do this and you expand, Taylor expand the x to the 4th term, you have signs. And luckily you have them because the result is finite. But if you have lambda which is negative, then the signs are all positive and the result is infinite. So this is what's happening here, but in a functional way that is completely out of control. So morally, if I had here a plus 1/2 instead of a minus 1/2, I would bet that the result is infinite just like this. But the point is that how to be so under control that the signs you know that they are not doing troubles. Just like in many other cases.
Okay, so I think we, at this point, should thank the